Okay, in this segment we're going to be talking about the CMOS analog of the emitter follower circuit, which is called the source follower. And this circuit consists of two transistors. We're going to use the NMOS version here, and then later by extension we'll talk about the PMOS operation, but we have VDD connected up here to the drain of the top transistor, and we have the output is the source of the top transistor, and we have the input coming into the gate of the top transistor, which we're going to call MSF. So it's customary to use M to denote a MOSFET, whereas it's customary to denote Q, a bipolar transistor, by Q. And we're going to call this MB, and we're going to call this VB. So this is, the B stands for bias transistor. And this is the bias voltage. And the job of the bias transistor, just like in the emitter follower, is to set up the current flowing in the source follower transistor. So this is the source follower transistor. And here we're going to be making our standard sorts of zeroth order assumptions. We're going to assume the transistors are matched, operating the same temperature. We're going to assume that the transistors are idealized. In the context of the MOSFET, that's going to mean that the early voltage is infinite, so no early effect. Okay, we also want to assume, for proper operation, MBX as a current source. That means MB operates, should operate, saturate in saturation. So it should be saturated. Okay, and that means in practice V out, which is the drain voltage of MB, should be greater than or equal to VDS sat. Okay, so it's going to be a constraint. We want to get a feeling for how this circuit works. First of all, before we start writing some equations and trying to solve for the voltage transfer characteristic, which is what we're going to wind up doing. In order to do that, I'm going to erase some of these words here. And what we want to do is kind of try to get a handle on qualitatively how the circuit is going to operate. And so we're going to do a thought experiment. Okay, so what we're going to do is connect the output to, let's say, a voltage source that's going to hold its value at plus 5 volts. So this is V out. And let's say that the input voltage is held at, let's say 2.5 volts. And we're going to set VB to be around the threshold voltage, let's say maybe like 0.6 or 0.7, let's say 0.7. so that IB is on the order of 1 microamp. Okay, that would be a typical threshold current. Well, and we're going to assume that our VDD is 5 volts here too. So let's think about the state of the circuit in this case. Okay, so clearly with 5 volts on the drain of MB, MB will be in far up on its drain characteristic. It's going to definitely be saturated. Okay, and so it's going to be acting like a constant current sink, pulling 1 microamp of current, almost independently of the output voltage, given that we're neglecting the early effect. And let's think about how much current is flowing in the source-follower transistor. Okay, so we have the gate at 2.5, the drain is up at 5, and the source is also up at 5. So we have a negative 2.5 volt gate to source voltage. So if this transistor passes very, very little current with 0 volts on the gate to source, then this is going to be passing practically no current, right? So the current through this transistor this pen is somewhat tired. So this current is, for all intents and purposes, about 0. Okay, it's going to be some very small number, like, 100 femtoamps or something like that, but it's negligible, certainly compared to 1 microamp. So this 1 microamp of current is not coming from the source-follower transistor. Where is it coming from? Well, it has to be coming from and supplied by this output voltage source that we're using to hold the voltage at +5. Okay? So what we're going to do is start the circuit in this known condition and release the output and think about where it goes. Okay? So let's imagine then we disconnect the output. And let's take this out here. And we have still the out at about +5 volts. Right, but now that 1 microamp has no place to come from. And so where is it going to come from? Well, it can't come from the source-follower transistor, because when the output is at about +5 volts, that means the transistor still is back-biased by -2.5 volts between the gate and the source. So its current is still going to be 0. So where is this 1 microamp going to come from? Well, it's going to come from a parasitic output capacitance. Right, so this is something we talked about back with a simple current mirror, and we're going to make use of it here too. So there's some C out, some parasitic output capacitance. This would not necessarily be an explicit capacitor in our circuit. This would be a capacitance that comes for free with the structure. We can't avoid it. So that 1 microamp of current is going to come from the capacitor and supply the 1 microamp of current required by the bias transistor MB. So initially, IB supplied by C out. So C out, though, IC is going to be C dV out dt, and that's negative. It's coming out of the capacitor to supply the transistor's current, and so that means that dV out dt is going to be less than 0 volts per second. It's going to be negative. And that has the implication, right, a negative time rate of change means that Vout is going to decrease. Okay, so Vout starts falling. So maybe Vout is now, 4.5 volts. Well, has the state of the circuit changed? Well, no, MB is still operating in saturation. It's a little less far up its drain characteristic, but it's still saturated, still requiring 1 microamp of current. We still have minus 2 volts on the gate to source voltage here of MSF. So that's still back biased, and it's still not going to be supplying any appreciable current, certainly nowhere near a microamp. And so this continues. This gets down to maybe plus 4 volts. And so we're still in the same kind of state, same situation, only now we have minus 1.5 volts gate to source. Let's jump down to, let's say, plus 3 volts. Still in the same situation. MB is still saturated, still requiring 1 microamp. Our source follower transistor is still back biased by minus 0.5 volt now. Still not doing anything. So it still continues to draw current out of the node capacitance. Vout still falls. And so now let's say we're down at 2.5 volts. Well, now we're at 0 volts gate to source voltage on the source follower transistor. So now the transistor is just kind of off instead of being back biased. But it's still carrying very little current, certainly not a microamp of current. And so IB will continue to come from the node capacitance. Now we get down to 2.4. Well, now we start to get a plus 100 millivolts gate to source voltage here, but still the current is going to be very, very small. If you recall from your Lab 5 gate characteristics, the current might be only a picoamp or something like that at maybe 0.2 or 0.3 volts on the gate to source. And so it's not until we get up to about maybe, 2.1 volt, where this might be like 10 picoamps. But this is still going to be, mostly 1 microamp coming from the node capacitance here. Okay, so now this will fall down a little further, 2 volts. Now we're at plus 0.5 volts gate to source voltage. Maybe this is up to 100 picoamps. Still nowhere near microamp. Okay, it's not going to be until this gets down to maybe about 1.6 volts, where now we're up in the territory of maybe 100 nanoamps or so. And now, now this is maybe at 0.9. And it may not be until about 1.5 volts, where this is now at 1 microamp. And now that static current coming from the source follower transistor is sufficient to supply all of the current flowing in the bias transistor. So at that point, that's when the output voltage stabilizes. Okay. Now it's true that we have here 0.7 volts VGS, and this is a matched transistor, so you might expect that there should be 0.7 volts VGS here. In practice, because of the body connection, because the source to bulk voltage of this transistor is higher than the source to bulk voltage of this transistor, it actually takes a little bit more VGS here to supply the same current, or to get back to the same current level. Turns out that that's going to be related to kappa, as we'll see. Okay, but that's how we can think about how the circuit gets into its operating point. Okay? So now what I want to do is do a slightly different thought experiment, and that is, suppose I am in this state, 2.5 volts on the gate, on the input, 1.5 volts on the output. And then suppose we increase V in. Suppose we make V in now, oh, I don't know, 3 volts. So we step it up from 2.5 to 3 volts at some time. Well, what's going to happen? Well, the output here is instantaneously at 1.5 volts. Okay. And it hasn't gotten the memo that the gate has increased to 3 volts. But doing that will result in a very large increase in the current here. So 5 volt, half a volt on the gate in around threshold might mean that this might go up to, I don't know, 50 microamps or something. And now we have 50 microamps flowing in the source follower transistor, and it's going to flow out of the source follower transistor onto this node. We only have 1 microamp being sunk by the bias transistor. Well, what's going to happen? Well, that excess current is going to have to be taken up by the node capacitance. So we have 49 microamps going into the output capacitance. So that means that IC, that's greater than 0. That means that dV out dt is greater than 0. That means that V out is going to go up. Okay, so V out will go up. Say it goes up to 1.6. Well, now we've turned down the current maybe by, oh, I don't know, a factor of 10. Maybe not quite a factor of 10. Maybe it's going to be, I don't know, 20 microamps. And that means that we now have only 19 microamps going into the output capacitor. But still, this 1 microamp isn't changing because the output voltage is just moving back and forth on a constant current source type of curve, characteristic. And so maybe this is going to go up to, well, I don't know, 1.7. And maybe by the time it gets up to 1.7, this has gone down to, I don't know, maybe 5 microamps. Still, or this has gone down to 5 microamps, still we have, let's say, 4 microamps going into the node capacitance. Well, still going to increase V out, maybe a little more slowly now. Let's say this goes up to 1.8, and this just is now down to 1 microamp. And so these currents now will balance each other statically, and no extra current goes into the output capacitance, and dV out dt is 0. That means V out has reached a new steady state. Right, so the source is going to go up. The output voltage is going to go up until it reaches a new constant value. So if V in goes up, V out goes up. It follows, the source voltage follows the gate voltage. Okay? Now we could tell a similar story about stepping the voltage down or decreasing V in, and that would turn this transistor off relative to where it was, and that means that current would have to flow out of the node capacitance, and that would decrease V out. So it's just like the initial state that we put the circuit in to figure out what the initial output voltage was. Okay? So that's a way of kind of thinking your way through how a circuit behaves. And that's a good thing to be able to do and to practice, to develop some intuition for how a circuit works. I just wanted to try to illustrate that before we start writing some equations and doing some math. Okay? So what we're going to do is we have to think about the operating mode of the source follower transistor before we can really start to do the analysis that we want to do. Okay, we said that we want the bias transistor to operate in saturation, acting like a constant current source. And we're going to assume that that's going to be true and then go back, just like we did with the emitter follower, and query that assumption and see where it's consistent, where the result of the analysis is consistent with that assumption. But first I want to go and talk about the source follower transistor. So given that the output voltage follows the gate voltage, the worst case scenario that we would have, if we assume that, further assume that Vn is in the range of 0 to VDD, right? So it's in the power supply voltage range. That's something I forgot to put in here. Worst case scenario for the voltage across this transistor would be, so at its lowest, that would be the worst case with respect to whether the transistor is operating the ohmic region or the saturation region, would be when Vn is at VDD. So smallest VDS across MSF is when Vn equals VDD. Right, that's the worst case. For saturation, for operation in saturation. Because for any lower Vn, the transistor will be up further in saturation with more voltage across it. Okay, so at this point, MSF is effectively diode connected. So the gate is at the same potential as the drain, and it's carrying the bias current IB. Right, so the question is, does the diode connected voltage transistor operate in saturation? The answer is yes. Just like the diode connected BJT operates in the active region. And the easiest way for me to show you that is to look here at this pair of slides. So in this slide, we have a family of drain characteristics, like you're looking at in Lab 5. These are up here in strong inversion, where it takes more voltage across the transistor to saturate it. And these are down here in moderate inversion, where the VDS sat is starting to increase a little bit. And then these are all down in weak inversion, where the VDS sat is about 0.1 volts or so. Okay, so VDS sat is independent of current level down here. And what we're going to do is, on this same graph, superimpose the diode connected transistor's IV characteristic. And what you can see here is that unless you get way, way, way down in weak inversion, this is like the gate characteristic, actually, by the way, of the transistors that you've been looking at. Unless you get way, way, way down in weak inversion, like below a picoamp of current, the gate to source voltage that you need is going to exceed the 0.1 volts that it takes to saturate the transistor. So the basic idea is that unless the current through the transistor is on the order of reverse junction leakage, like on the order of, let's say, femtoamps of current, the diode connected transistor will operate in saturation, where the gate to source voltage on the diode connected transistor, the diode drop at whatever current level we happen to be operating at, is to the right of, i.e. greater than, the VDS sat voltage, which is this dashed line here. Okay? So the source follower transistor will always operate in saturation. now we know what to assume about the source follower's IV characteristic. We're going to assume that MB operates in saturation, and we're going to use the EKV model. Okay. So KCl tells us that the current flowing through both transistors is going to be the same in the steady state. So IB, so EKV, the EKV model tells us that for MSF, let's say EKV at MSF tells us that IB is going to be IS times log squared 1 plus e to the kappa times Vn, that's the gate voltage, minus VT0 minus the source voltage, which is V out, over 2 UT. Okay, that's the full EKV model for the saturation current, specialized to MSF. The EKV model at the diode connect, or at rather the bias transistor, tells us that IB is also equal to IS times log squared 1 plus e to the kappa VB, that's the gate voltage down here, minus VT0. Now the source voltage is connected to ground, so we don't have the source voltage there, over 2 UT. Okay, so the matching tells us that these two transistors have the same parameters, the same IS value, the same kappa value, the same VT0. The fact that it's operating at the same temperature tells us that the UTs are the same. And so what we're going to do is we're just going to basically unpeel all the layers of the onion. Okay, so we can cancel the IS's. So setting these two things equal, we can cancel the IS's. From both sides of this equation, IB equals IB, right? And then we can take the square root of both sides. That undoes the square. We can take the log of both sides, or rather exponentiate both sides, so we take the cancel IS, take the square root of both sides, exponentiate both sides, that undoes the log. So now we have 1 plus e to this stuff is equal to 1 plus e to that stuff. Subtract 1 from both sides. That implies that e to the kappa Vn minus Vt0 minus V out divided by 2 equals e to the kappa Vb minus Vt0 over 2 UT. And we can take the log of both sides here. And so we get kappa Vn minus Vt0 minus V out over 2 UT equals kappa Vb minus Vt0 over 2 UT. Those cancel, and we get kappa Vn minus kappa Vt0 minus V out equals kappa Vb minus kappa Vt0. Minus kappa Vt0's cancel. We can solve for V out, and that is equal to kappa times Vn minus Vb. Okay, so this is one of the very few instances I know of where we can actually do a full-on large signal analysis of a CMOS circuit using the simplified EKV model and get a nice result that holds across all inversion levels. So it says V out is equal to kappa V in minus VB. What does that look like if we plotted that, the voltage transfer characteristic? Well, here's a plot of V out versus V in. And let's say this is VDD, this is VDD. Draw a box, draw the identity line. The slope of 1. And what this says is that when Vn is equal to Vb, V out is equal to 0. So let's say this is Vb here. So this is a line with an x-intercept of Vb and a slope of kappa, which is less than 1. And of course this continues with the slope of kappa down here. And the question is, where is this model valid? Well, this is valid for V out is greater than or equal to VDS sat. Right? And so we can take this model for V out and re-express this. So VDS sat might be something like that, 1/10 of a volt or so. We can re-express this expression here, this inequality constraint, in terms of V in by using this model, right? So this is kappa Vn minus Vb greater than or equal to VDS sat, which implies that Vn has to be greater than or equal to VDS sat, well, VDS sat, let's say VB plus VDS sat over kappa. Okay, so basically that the actual characteristic would do something like the emitter-follower characteristic does. It basically flattens out and goes to 0 here as the bias transistor operates in the ohmic region. And so this is where MB is saturated, and this is where MB is ohmic in terms of the input voltages. So this implies a certain minimum value that we can allow on Vn in order to keep the bias transistor saturated. Okay, I want to show you a source follower characteristic, a measured source follower characteristic from an ALD11. What I want to do is this, and I want to switch over to this. So this is a measured source follower characteristic from two ALD1106s, where I've set the bias voltage here to be at threshold, and I've set the bias voltage to be somewhat above threshold here. And you can see that these two characteristics look very much like we sketched. When we extrapolate this back down here, the x-axis intercept is about 0.7 for that one, and here if we extrapolate this back down, it's about 1.2. So that's all good. You can see that the slope of these two lines here are very similar. They are very parallel to each other. At least they appear parallel to each other. The other thing you can see here is that the approach here to 0, as we get MB into the ohmic region, is much sharper down here for the at threshold or the moderate inversion VTC, whereas here for the strong inversion VTC you can see it's more rounded. It takes longer, it takes more voltage to approach 0, and it's more gradual. And that's characteristic of strong inversion type circuits. Anyway, so you can see that qualitatively the behavior of these two source follower characteristics are the same, with that sort of more rounded behavior for strong inversion, but the kappa values are very similar to each other. So that's going to be it for this segment, and we'll talk about the PMOS source follower in the next segment.